Hey guys! Today we're going to practice integrating in spherical coordinates, including how to identify when our integrals should use spherical coordinates and how to set up our limits of integration from a problem. So for today, I have this example problem. I want you guys to, we together want to compute the integral over this region E of 1 over the square root of x squared plus y squared plus z squared dv, where E is the right half of a sphere of radius 4. What do I mean by the right half of a sphere? Well, I mean, we're telling you it's along the x-axis, so that means we're sort of cutting at the yz plane, and we're taking the part along the positive x-axis. So if I want to draw that, it would look something like this, where I've got my x and my z and my y sort of going in, and my sphere is centered at the origin. I know it doesn't say it, we're sort of like implying it. So it would look like this, where the radius of this half sphere is 4, if that makes sense. Okay. So right away, looking at the picture, we see, okay, this thing is half a sphere, so spherical coordinates are probably going to be the way to go. There's another way to see that from the actual integrand of the problem. So our integrand is, remember, the part that we are integrating without the differential and without the limit sign. And we see inside of there, we've got x squared plus y squared plus z squared, which we remember is actually rho squared, where if you're in a physics class or if you're looking at some other source, we might also call this r squared, where now rho is the radius of our sphere versus, so this is in spherical coordinates. In cylindrical coordinates, you'll recall we had just x squared plus y squared was r squared, and we kept z was z. The reason for that is because here rho is the radius of a sphere, so it's the distance from our point xyz to the origin, whereas in cylindrical coordinates, r is the radius of the circle, and we're cutting it parallel to the xy plane, so it's just the distance to the z-axis instead of to the actual just origin. All right, and we see x squared plus y squared plus z squared, so that tells us to use spherical coordinates, and we actually have the square root of them, so I can just take a square root of both sides, and I know that rho is always positive, so I just need to take the positive square root, right? It's positive because it's a distance, and distances have to be positive, or at least non-negative. Okay, so that means that our new integrand, let's just copy our integral that we're trying to compute. I can replace the pink with just 1 over rho. So I still haven't figured out my limits, so I'm still just integrating over E, but now I'm integrating 1 over rho dv. Okay. So it's already shaping up. Looks a little bit simpler. Next, we have to figure out what is our differential v. Let me just fix that so it looks a little bit clearer. And what are our limits on our integrals. So recall that the differential volume element is d rho times rho d theta. We recall that from even in cylindrical and polar coordinates, we always have to add an r, a radius, but in this case, r is rho. And then when we add our third differential piece to get a volume element, we have rho sine phi dv. Now, let's be careful here. If you're in another class where we're doing triple integrals, maybe if you're taking a physics class, physicists often reverse theta and phi. So here, phi is the angle from the z-axis. Highlight that. One's phi. We don't highlight it there. And theta is the angle in the xy plane. So they're different. We need to keep track of which one's which, and it does matter because we see a sine of phi here. We don't see a sine of theta, and if you change it, you'll get a different answer. All right. So let's go ahead and plug that in for dv. We may want to solve it so that we have all of our differentials at the end. So we just get rho squared sine phi, d rho, d theta, d phi. We're just going to plug that in. Sine phi, d rho, d theta, d phi. Okay, looks good so far. It's shaping up to be a nice doable integral. The only thing we're missing now is the limits of our integral. So we like to figure those out from right to left. So we're going to start by figuring out our rho limit. And I'm going to go ahead and simplify 1 over rho times rho squared is just rho. And then we keep the sine phi, d rho, d theta, d phi. All right. So what are our limits? Keep our question in the frame. What are the limits of our integral for rho? Well, what is the minimum radius that we are looking at? Well, the radius is smallest at 0 because that's the origin. The origin is in the region E. So we're definitely starting at 0. And then what is the maximum? Well, the maximum should be 4 because remember, we're just integrating along this half sphere, and this sphere has radius 4. The whole sphere would have radius 4. Very bad circle. All right. So we figured out the limits for our rho integral, our radius integral. Now we need to figure out the limits for our theta integral. Remember, theta is the angle in the xy plane. Now our lowest, since we recall we measure from the positive x-axis, it's going to be negative down here. And we're sort of cutting when y is -4 and x is 0. And that corresponds to the angle negative pi over 2 radians. And then our maximum is the 90-degree angle, which is pi over 2 radians, positive. And this makes sense because the distance between negative pi over 2 and pi over 2 is pi. And pi is exactly half of a circle, which is what we're looking at. We cut a sphere in half, so we're looking at half of a circle when we take that cross section. And then lastly, we need to figure out the limits of our integral with respect to phi, which remember is the angle measured from the positive z-axis. And we do include the positive z-axis, so we start from 0. And we go all the way down to the negative z-axis, which we see was 180 degrees, was pi radians. So we integrate from 0 to pi. And now our integral is totally set up. All we have to do is actually figure out what it is. So let's go ahead and do the rho integral. So we are left with the integral from 0 to pi, the integral from negative pi over 2 to pi over 2. And we know that the integral of, well, sine phi is constant with respect to rho. So we just have sine phi out front. And the integral of rho with respect to rho is rho squared over 2, right? We're just using the power rule of integration. And we're evaluating rho from 0 to 4. And then once we've done that, we will do our other 2 integrals. So we're just going to keep those differentials out front. Maybe we'll put this in parentheses. Looking good. All right. If we plug in rho equals 0, that's just 0. So only the 4 limit will actually give us a term that doesn't go away. So we are left with the integral from 0 to pi, the integral from negative pi over 2, pi over 2. If I plug in 4, 4 squared is 16, over 2 is 8. Sine phi, d theta, d phi. Awesome. Let's do our next integral. Our next integral is the theta integral, and we actually don't have a theta in our integrand. And I know sometimes like this looks a little weird, but remember, everything else is just constant. And when we integrate just a constant, we just sort of get a theta out, right? Because the derivative of a constant times theta is the constant. So the integral should just add a theta as a factor, not as an addition. So we're left with 8 sine phi theta outside of the sign. And we are evaluating from theta is negative pi over 2 to pi over 2. And then we'll do our phi integral. Put some parentheses on that. Well, if I plug in pi over 2 minus pi over 2, I'm just multiplying by pi. So I've got the integral from 0 to pi of 8 pi coming from that theta sine phi d phi. Awesome. Now 8 pi is just a constant, so I can pull it out. And I'm just integrating sine phi. And I know that the integral of sine is negative cosine, because I know that the derivative of cosine is negative sine. So I've got negative cosine phi. From phi goes from 0 to pi. And I know that the cosine of 0 is 1, and that the cosine of pi is negative 1. So I've got negative 1 is positive 1, minus negative 1 is plus 1. So I just get 8 pi times 2 is 16 pi. And that is the whole problem. So in this problem, we were asked to identify what coordinate system we should integrate over, and we determined that it was spherical because we saw x squared plus y squared plus z squared, and because our bounds were a part of an integral, we're a part of a sphere. Additionally, we had to recall what our differential volume element was for spherical coordinates, plug it in, and figure out our limits from the problem. That was it.